All right, so we are here Thursday, September 24th. We're going to finish chapter 2, going beyond polynomials, sections 2.6 and 2.7. But remember that chapters 2 and 3 are in a huge homework assignment. Chapter 2 and 3 are in a big homework assignment, worth about as much as the first two put together. Okay, and they're going to be due, I guess, Friday, October 9th, looks like. Okay, we'll have the whole day discussed it the day before on the 8th. All right. In the meantime, I hope to get a lot of grading done over the next few weeks. Remember, starting on Tuesday, I'm going to start reusing my videos from spring. I looked them over. The videos seem good, although you can see me kind of experimenting along the way. All right. All right. Any general questions? All right. So let's start off. Hi, everyone. So far, we've been looking at polynomial function rules like these. Now we're going to look more generally at rational function rules, which include polynomial function rules. So now we're going to look at things more like 1 over x. In section 2.6, we're going to look at rational functions in general. We got a small taste of this in section 2.3 when we studied polynomial division. For example, when we were considering expressions such as these, where we had this polynomial over this polynomial that was not 0. This is an example of a rational function rule that's not polynomial. So for now, in section 2.6, let's assume that f of x is a rational function rule, and it's written as a polynomial over a polynomial that's not 0. And for now, let's assume that this is in simplified form. Later on, we're going to relax that assumption. But for now, assume that this expression is simplified. So no factors like x, for example, in common. No real zeros in common either. Now, unlike for polynomial graphs, sometimes graphs for rational functions have vertical asymptotes, or VAs. Remember that an asymptote for a graph is basically a line that the graph approaches. For a VA, it's a line that the graph approaches in an explosive sense. The function values, or y-coordinates, approach either infinity or negative infinity as you approach the vertical line. So for example, remember how to graph y equals 1 over x. That was this hyperbola, and we had a vertical axis at the y-axis, or x equals 0. We had a VA, a vertical asymptote, at x equals 0, this blue line. Normally, however, asymptotes are normally dashed. It's a vertical line that the graph approaches. That's the case whether we had just the quadrant 1 branch or just the quadrant 3 branch. Now, what about the graph of y equals 1 over x minus 2? What happens to the graph of y equals 1 over x when we replace or substitute the x with x minus 2? Remember that? We translate the graph to the right by 2 units. So we go from the red graph over here to the green graph over here. And not only does the graph translate, but also the vertical asymptote. We move from x equals 0 as the vertical asymptote to x equals 2 in purple. So the VA moves from x equals 0 to x equals 2. On the left, we have the graph of y equals 1 over x. We have a VA at x equals 0. On the right, we have the graph of y equals 1 over x minus 2. The VA is at x equals 2. If we had 1 over x minus 3 guess where the VA would be? The VA would be at x equals 3. If we had 1 over x plus 1, where would the VA be? At x equals -1. Basically, at the real 0 of the denominator. Remember, we're assuming that the fraction is simplified. So when we have 1 over x minus 2, the graph of y equals 1 over x minus 2 has as its only VA x equals 2, which corresponds to the only real 0 of the denominator. In general, if you have a simplified rational expression like this in x, polynomial over polynomial, then the VAs, the vertical asymptotes, correspond to the real zeros of the denominator. So for example, y equals 1 over x minus 2, we have a VA at x equals 2. Now in calculus, you define vertical asymptotes more precisely using limits. Take a look at this graph on the right. Y equals 1 over x minus 2. Observe that as we approach the vertical line x equals 2 from the right, the y-coordinates along the graph, the function values, approach infinity. In calculus, we'd say that the limit of f of x as x approaches 2 from the right is infinity. Look at this branch over here. As x approaches 2 from the left, the y-coordinates or function values approach -infinity. So we would say that the limit of f of x as x approaches 2 from the left is -infinity. So therefore, x equals 2 gives us a vertical asymptote. Now, we have a vertical asymptote, a VA, at x equals 2, if either of these limits is either infinity or -infinity. So whether we had this branch alone, or this branch alone, or if we had a piece of the graph that went like that, or a piece of the graph that went like that, we'd have a VA at x equals 2. Now sometimes, like when we have logarithmic functions, like y equals ln of x, here, the VA is only relevant from one side, and that's fine. That's related. Next up, we're going to consider, well, HAs, horizontal asymptotes. And the analysis is completely different, the way we find them.
But first, we're going to do some more VAs. Any questions so far? Any questions so far? All right.
Hi, everyone. Before we start with HAs, let's classify VAs, vertical asymptotes. First, let's review this exercise from section 2.5. We factored this polynomial over the reals, like so. And we found that 0 was a 0 of multiplicity 3. Look at the x cubed over here. And we also found that 4 was a 0 of multiplicity 2. Look at this, the square of x minus 4 over here. Notice the leading term is x to the 5th. Based on this information, sketch the graph of y equals f of x. I'll give you 20 seconds. All right, let's see what Desmos has to say. So let's try y equals x to the 5th minus 8x to the 4th plus 16x cubed. I could have also entered the factored form over here. Well, that's what we have here. So overall, we have a rising snake. That's no surprise if we zoom out. Okay. And we have two x-intercepts. we have an x-intercept at 0, 0, right? And the multiplicity of 0 as a 0 was 3. It was odd. So that's why the graph cuts like a snake around this x-intercept. And notice here that the graph is particularly flat around the origin. The multiplicity is 3, not 1. Because the multiplicity is higher, we have more flatness here, more flatness near the origin. Now, what about the point 4, 0? We have an x-intercept at 4, 0. The multiplicity is 2. That means we have a bounce. All right. So we have a cut at the origin, 0, 0. And it's pretty flat because the multiplicity is pretty high. It's 3. It's odd, so we have a cut here. The multiplicity for 4 as a 0 is even, 2. So we have a bounce here. Overall, it's a rising snake. Now, the multiplicities here tell us about cutting versus bouncing on the x-axis, at the x-intercepts. But what if these factors were in the denominator? Ah. So what happens then? What if we have y equals 1 over x? Is this hyperbola? And the y-axis, x equals 0, is a VA. And in this case here, because as x approaches 0 from the right, this branch has y approaching positive infinity, and as x approaches 0 from the left, the y approaches negative infinity. So notice that the two branches are going in opposite direction. Y approaches positive infinity from this direction, y approaches negative infinity from this direction. Split infinities, split directions. For that reason, we call this asymptote in here, the y-axis here, an odd VA. Because you have these split behaviors around the asymptote. In general, if you have an odd exponent on the corresponding factor for x down here, you're going to get an odd VA. So 1 over x cubed, again, we have an odd VA. If we have 1 over x minus 1, all to the third, then we have an odd VA at x equals 1, where the branches go in opposite directions. This time around the VA, x equals 1. So an odd exponent on the factor here, the multiplicity of a 0 in the denominator, if it's odd, then we have an odd VA. Now what if it's even? What if we have y equals 1 over x squared? How did the graph of y equals 1 over x squared look like? It was a basic graph. It was this volcano graph. But once again, the y-axis, x equals 0, is a VA. This time, however, the branches are going in the same direction. As x approaches 0 from both the right and the left, y, or the function value, approaches positive infinity in both cases. So here, the VA is an even VA. And that corresponds to the fact that we have an even exponent on the factor here. 0 is a 0 of the denominator with multiplicity 2. Likewise, if we had x minus 1 all squared down there, then we would have an odd VA at x equals 1. I'm sorry, an even VA at x equals 1. For that matter, if we put a minus sign in front, an opposite sign, well, both these branches go down, but they're both going in the same direction. The y-coordinate, the function value, is approaching negative infinity as x approaches 0 from the left and from the right.
All right, any questions? Any questions? So the multiplicities on the top give you cutting and bouncing. The multiplicities on the bottom give you odd and even VAs. Any questions? Questions?
Hi, everyone. We're now going to look at horizontal asymptotes, HAs. An HA is a horizontal line that a graph approaches in a long-run sense as x approaches either infinity or negative infinity. So let's say that we have the graph of y equals f of x, where f of x is written like this: a polynomial in x over a polynomial in x, not 0. In fact, it doesn't even matter anymore if it's simplified. Now, when do we have an HA at y equals a number, L? Remember, we have a horizontal line when we have something like y equals 0, y equals 1, y equals 2, and so forth. So when do we have an HA at y equals a real number, L? Well, by definition, that happens if and only if and only if the limit of f of x as x approaches infinity is L. So this long run limit is L. Or the limit as x approaches negative infinity is L. If either of these is true, then there's an HA at y equals L. Now, in general, it's possible that the graph of a function could have two HAs. That is actually possible. If you have the graph of y equals a function of x, you could have actually two HAs. For example, y equals the absolute value of x over x. We have an HA at y equals 1 that's relevant to the right, and we have an HA at y equals negative 1 that's relevant to the left. However, this is not a rational function. For a rational function, the graph can have at most one HA. So it could have 0 or 1 HAs if you have a rational function. If you have a non-rational function, you could have as many as 2. Okay. Now let's take a look at the most basic example where we have an HA. Y equals 1 over x. Both branches will approach a horizontal line, namely the x-axis, which has equation y equals 0. Again, normally HAs are dashed. The y-coordinates or function values approach 0 off forever to the right, and the y-coordinates or function values approach 0 off forever to the left. Now, in fact, if we have y equals 1 over x squared, again, we have an HA at y equals 0. Y equals 1 over x cubed. Y equals 1 over x to the fourth. In fact, anytime we have case 1 applying, where the degree of the numerator is less than the degree of the denominator, or in other words, the degree of the denominator is greater than the degree of the numerator, I call this the bottom-heavy case by degree. The degree of the bottom is bigger than the degree of the top. Then we have a proper rational function in a similar way that 1/3 is a proper fraction. And y equals 0, the x-axis, is the only HA of the graph. So here's some examples of bottom-heavy cases. Y equals 1 over x, where we have degree 0 over degree 1. Y equals 1 over x squared, where we have degree 0 over degree 2. Or we could have something like x cubed plus 1, which is degree 3, all over x to the 5th minus 2. Now, the graph seems pretty messed up, close to x equals 0, but in the long run, we're approaching y equals 0. If you zoom out, we're basically getting something that looks like the x-axis going off forever to the right and forever to the left. Degree 3 over degree 5, bottom heavy. The degree of the bottom is greater than the degree of the top. Anytime this happens, we're going to have an HA at y equals 0. I don't even care if this is simplified. I don't care about the real zeros of the denominator, the way we did with the VAs. As far as HAs are concerned, we just care about the degree of the top versus the degree of the bottom. That's all that matters. So there's shortcuts. So again, for y equals 1 over x, 1 over x approaches 0 as x approaches either infinity or negative infinity. So that means that y equals 0 is an HA. If 1 over x approaches 0 in the long run, then y equals 0 is an HA, a horizontal asymptote for the graph. Basically, this happens where f of x is 1 over x and L is 0. But also, we can have something like this. F of x equals 1 over x squared plus 1. What's the degree of the top? The degree of the numerator, the top, is 0. The degree of any non-zero constant is 0. What's the degree of the bottom, the denominator? The degree of the denominator is 2. So again, we have the bottom heavy case. We have this case 1 here. And y equals 0 is the only HA of the graph. The x-axis is the only HA for the graph. By the way, if you have the graph of a rational function, if you have an HA that's relevant in one direction, that same HA must be relevant in the other direction. Unlike this guy over here that we saw earlier. That was not rational. Now, hint, hint, the x-axis is the only HA. Now, at this point, we can actually sketch the graph of this. Y equals 1 over x squared plus 1. Hint, the x-axis is the only HA for the graph, but you can also consider issues such as domain, x and y intercepts, symmetry, and also VAs, in addition to the HA we discussed. Based on these clues, try to sketch the graph. Oh, and there's another issue too, the issue of signs. The sign of f for various values of x. Go. I'll give you 1 minute to try to sketch the graph as best you can. We have some key hints here. All right. So let's start with the issue of domain. Now, we only have a problem when the denominator is 0. But wait a minute. If we try to solve x squared plus 1 equals 0, does that have any real solutions? The answer is no. So we never have a problem, and the domain is just R instead of all real numbers. Speaking of which, again, the denominator is never 0 for any real values of x. The denominator has no real zeros. The denominator has no real zeros, which means that the graph has no what? Real zeros of the denominator corresponded to VAs. No real zeros for the denominator, x squared plus 1, therefore no VAs. No VAs. But, as we mentioned before, there is an HA at y equals 0, the x-axis, because we have the bottom heavy case, degree 0 over degree 2. All right, now what about intercepts? What about intercepts? All right. Let's consider the y-intercept first. That's easier. For the y-intercept, we plug in or substitute x equals 0. Basically, we work out f of 0. F of 0 equals, when you plug in 0 for x, you get 1 over 1 or 1. Therefore, 0, comma 1 is the y-intercept for the graph. But now, what about x-intercepts? What about x-intercepts? Well, now we get x-intercepts when y, or this whole thing here, equals 0. We get an x-intercept if and only if the whole fraction thing equals 0. When 1 over x squared plus 1, the function guy, the fraction, is equal to 0. But wait a minute. When does a fraction equal 0? When does a fraction like this equal 0? When the top is 0 and the bottom isn't. But wait a minute. Can 1 ever equal 0? Can 1 ever equal 0? The answer is no. The top can never equal 0. Therefore, how many x-intercepts do we have? We have none. No x-intercepts. So to recap, 0, comma 1 is the y-intercept, but we have no x-intercepts. Symmetry. If you replace x with the opposite, what happens? Well, the square doesn't care, right? So f of x equals f of opposite x for all real values of x. F of x equals f of opposite x for all real values of x. Okay, all throughout the domain. Therefore, what kind of symmetry do we have? We have even symmetry, which means that the graph of this thing is symmetric about the y-axis. And finally, the sign of f. Look at this. 1 over x squared plus 1. That thing is always going to be positive, isn't it? So notice that f of x is going to be greater than 0 for all real values of x. Wow, we have a lot of information here. Let's piece it all together, all right? Here we go. This should do it. All right, here's why. First of all, domain is all reals. All real values for x coordinates are picked up. In particular, we have no VAs, right? We have no break-aparts here. All right, the domain is all real numbers. Intercepts, we have a y-intercept at 0, comma 1. We have no x-intercepts. In fact, the x-axis is an HA, a horizontal asymptote. It's like an electric fence. It's an HA that we never touch. Bear in mind, though, that sometimes you can touch the HA, which kind of freaks people out. Sometimes a graph touches or crosses over its own HA. There's a good example from trig. Y equals sine of x over x. For this guy, we have an HA at the x-axis, y equals 0. Right? But, okay, the graph does touch the HA. In fact, the graph touches and crosses over the HA infinitely many times, which surprises you because you're so used to things like y equals 1 over x, and you might think, oh, wait, it doesn't look like this graph touches as HA. Well, this graph doesn't, but there are other graphs, like this guy here, that do. In fact, there are rational graphs that touch and cross over their own HAs. We'll see that. All right, anyway. Here, in this case, we have no x-intercepts. The graph never touches the x-axis, which happens to be the HA. This particular graph never touches its own HA. Again, y-intercept at 0, comma 1, no x-intercepts. All All right. Wow, what else? F of x is always positive. That means that the graph always stays above the x-axis. That's why this bell shape is always above the x-axis, because the function values, the y-coordinates, are always positive. Symmetry, it has the even symmetry. We have symmetry about the y-axis. So it kind of makes sense that starting at the y-intercept of 0, 1, we approach the x-axis over here because the x-axis is an HA. We approach the HA, all right, y equals 0. We have symmetry. We also approach the HA in this direction. And because this function guy, y equals 1 over x squared plus 1, he's pretty simple. We don't expect this thing to be too wobbly. He's not that complicated. All right. So wow, lots of information there. Desmos does a better job of it, by the way. Let's graph y equals 1 over x squared plus 1. Again, the various features. Domain is all real numbers. We pick up all real numbers as x coordinates. This guy's always positive for all real x. This thing is always above the x-axis. The x-axis is an HA because this thing's bottom heavy in degree. We have degree 0 over degree 2. There are no x-intercepts. This particular graph does not touch its own HA, although in general a graph could do that. This graph does not touch its own HA. We do have a y-intercept at 0, 1. Again, we have even symmetry about the y-axis. It makes sense that we have this bell shape here. And we have no VAs. The fact that the domain is all reals is very consistent with the idea that we have no VAs. I mean, in principle, a graph could do something like this. Touch and then explode over here. But no rational graph does this, quite frankly. No rational graph does this. So the fact that we have no VAs, that's very consistent with the fact that the domain is all real numbers. Wow, all this information here. We know a lot. All this information here. Domain, intercept, symmetry, VAs and HAs, sign of F. A lot of information. We can do a good job of sketching the graph, and we only had a point plot, 1 point, 0, 1. We used our mathematical sense to sketch the graph without having to do any other point plotting besides this guy. All right. So this was another example of the bottom heavy case in degree, where the HA was at y equals 0, the x-axis. What if we have a situation where something like this is not bottom heavy? For example, in case 2, we'll look at the case where we have equal degrees on top and bottom next time.
Wow, a lot of information there and a lot of review. Any questions? Any questions? All right, let's take a look at the other cases.
Hi, everyone. What happens if the numerator and the denominator have equal degrees as polynomials? Then there is one HA, and it's at y equals L, where L is what number? Well, take a look at this. Consider f of x equals 4x cubed minus x over 5x cubed plus 1. The degree of the numerator is 3. The degree of the denominator is 3. We have equal degrees. So we have more of a fair fight. Before, the denominator totally beat up the numerator in the long run, and the whole thing was dragged towards 0. But here we have more of a fair fight. Now, it turns out that there's an HA. The only HA is at y equals 4/5, or 0.8. Where do we get the 4/5? Where do we get the 4/5? And why does that make sense? Why does it make sense that the HA is at y equals 4/5? Well, 4 is the leading coefficient of the top. 5 is the leading coefficient of the bottom. 4/5 is the ratio of the leading coefficients in order. It's the ratio of the leading coefficients in order. Now, why does that make sense? By the way, here's a graph, y equals 4/5 or 0.8. This graph approaches the line in the long run. Notice this graph touches the HA, that's legal. This graph touches and even crosses over the HA, that is legal. Now, why does that make sense? Why does it make sense that y equals 4/5 is an HA? Because look here, this is informal. You'll analyze this more precisely in calculus. But the top is dominated by the leading term, 4x cubed, especially in the long run. The bottom is dominated by its leading or dominant term, 5x cubed, especially in the long run. So in the long run, as x goes out to plus or minus of millions, billions, or trillions, we're basically dealing with 4x cubed over 5x cubed, which is pretty much 4/5. So if x is going out to the millions, billions, trillions, you're basically talking about 4/5, give or take a little. Let's have Desmos graph this thing, by the way.
Too many screens.
So we have y equals 4x cubed minus x all over 5x cubed plus 1. If I zoom out, let's say we look at this thing from Mars. It basically looks like a horizontal line. And there's a VA that looks like a vertical line. That is a vertical line over here. So in the long run, this thing looks like a cross. There's an HA here and a VA there. Looks like a cross if you look at it from Mars. And where's the HA? It's at y equals 4/5 or 0.8. I'll flash it. The red graph really approaches the blue graph in the long run. In fact, in the long run, it basically looks like the blue graph. The vertical line here is the VA. So in the long run, this thing looks like a cross. Okay. So if I ask you to plug in x equals 1,000,000, it's going to be pretty much 4/5, give or take a tiny bit.
All right, any questions? Any questions? Play with Desmos. Here we have the top-heavy case.
Hi, everyone. So how do we deal with the last case, case 3, the top-heavy case, where the degree of the numerator is greater than the degree of the denominator? Well, my short answer for you is that there are no HAs. But then, what is the long-run behavior of the graph of such a function? Before, when we had an HA, we knew the long-run behavior. For example, in case 1, y equals 1 over x, bottom heavy. We knew that the HA was at the x-axis, y equals 0. And in the long run, as x got extreme, basically we got y equals 0. So that told us the long-run behavior of this graph and this function. But what happens in the top-heavy case? Well, here's an example. It's the zoom-out property. Back in section 2.3, we performed long division on this problem. This third-degree polynomial divided by this second-degree polynomial. This is in the top-heavy case. So we know that there are no HAs. But what will be the long-run behavior of this function? What happens if we try to graph this thing? Let's perform the long division. In fact, we already did it in 2.3. So when we did that, first we put these parts in descending powers. We performed the long division, the divisor on the outside, dividend on the inside. And this was at the end of this main phase, where we got this polynomial quotient 2x plus 1. We got this remainder, negative 2x minus 6, and that ultimately goes over this divisor, the 3x squared plus 1. We can ignore the 0x at this point. So when we perform the long division, we get, once again, the polynomial part, the quotient, 2x plus 1, plus the negative 2x minus 6. I popped out the negative 1 factor. So minus the fraction positive 2x plus 6 over 3x squared plus 1. That was the result of our long division. Now notice, we were dividing a third degree guy by a second degree guy. It's no wonder our quotient is first degree. The quotient we get, the polynomial piece we get here, has as its degree the difference of the degrees here. The degree of the top is 3. The degree of the bottom is 2. So the degree of the quotient is 1. It's a linear quotient. Now, what about this fraction over here? Well, if you've done your long division correctly, either your remainder is 0, or you have a piece here that does what in the long run? Hey, if you've done your long division correctly, either you get 0, or you get a situation where the top, the remainder, has as its degree a number less than the degree of the denominator. In other words, this fraction better be what? This fraction better be bottom heavy. If you've done your long division correctly, you either get 0 or you get a top, a remainder, whose degree is less than the degree of the bottom. It's a bottom heavy rational expression. And in the long run, as x approaches either infinity or negative infinity, what happens to the value of this bottom heavy guy? It's going to approach 0. Because if you graph this separately, you get an HA y equals 0. This whole thing approaches 0 in value in the long run. Because remember, HAs don't tell you about graphical properties. The HA also tells you what number, what value this thing approaches in the long run. Bottom heavy guys like these approach 0 in the long run as x gets more and more extreme.
Don't
so
just
in the long run, again, as
I meant don't just tell you about graphical properties. It also tells you about graphs and numerically what's happening.
0 in the long run as x gets more and more extreme. So in the long run, again, as x approaches plus or minus infinity, the graph of y equals f of x will approach, the graph of y equals f of x will approach the graph of y equals the quotient, 2x plus 1. Because this fraction piece either is 0 or it's going to approach 0 in the long run. Its impact is going to die in the long run. And the 2x plus 1 dominates. Really, the 2x dominates. So in the long run, what should this graph look like? It should look like a line, a slanted line of slope 2. This is called a slant asymptote. Y equals 2x plus 1 is a slant asymptote or an oblique asymptote. It's a slant or oblique asymptote. It's a slanted or tilted line that the graph approaches in the long run. Okay. Now, bear in mind that the graph of a rational function, a rational graph, cannot have both an SA and an HA. The only way you have an SA is if you're top heavy. In particular, if you're top heavy by how much in degree? If you're top heavy by 1. So the only time you get an SA is if the degree of the numerator is specifically 1 more than the degree of the denominator. Then the quotient is degree 1. It's linear. Okay? In the long run, we get that. Let's graph this. Let's graph this original guy over here using Desmos. All right. So let's graph y equals, parentheses, negative 5 plus 3x squared plus 6x cubed, parenthesis, right arrow, parenthesis, all over, parenthesis, 1 plus 3x squared, right arrow, parenthesis. All right, so is this graph in black? In the long run, it looks like a line, specifically the line y equals 2x plus 1. Quite frankly, even the plus 1 doesn't matter that much. But technically, the slant asymptote is y equals 2x plus 1. But we know that just like y equals 2x plus 1, this graph is going to approach, y will approach infinity as x approaches infinity, like over here. Y approaches infinity as x approaches infinity, and y approaches negative infinity as x approaches negative infinity. It's kind of like a snake graph almost. Well, actually, it is approaching a linear snake. It's kind of approaching a linear snake.
Whoa, 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 wait, whoa, whoa. Whoa, what happened? Okay. Sorry, let me try to retrieve that. Oh, here we go.
Hi, everyone. So how do we deal with the last case, case 3, the top-heavy case, where the degree of the numerator is greater than the degree of the denominator? Like over here. Y approaches infinity. What if I put 6x? All right.
Okay, there we go. All right.
But notice here, the graph actually does touch and cross over its SA. Again, there was nothing that stopped the graph from doing that. This graph does touch and cross over its own HA, and there's nothing that stopped it from doing it. Just like there's nothing that stopped the graph from touching or crossing over an HA. All right. Now here's my question to you. Instead of 6x cubed, what if I put 6x to the 4th? What if instead of 6x cubed, I had 6x to the 4th? If you take, hypothetically, if you take a 4th degree polynomial and you divide it by a 2nd degree polynomial, the quotient will be what degree? Well, the difference of the degrees, 2nd degree. 4 minus 2 is 2. A 4th degree divided by a 2nd degree will always give you a 2nd degree polynomial, maybe with this fraction piece over here. All right, which means in the long run, since you're going to get a 2nd degree quotient, in the long run, if we had 6x to the 4th over here and the rest stayed the same, what will this graph look like in the long run if we had 4th degree over 2nd degree? Let's take a look. Let's make this a 4 up here. And we get, drum roll please, we get, in the long run, a bowl. A bowl. Because the quotient is going to be 2nd degree, and it's going to graph like a parabola. If you just graph the quotient piece, the polynomial piece, it's a parabola. In fact, some books would call the quotient an oblique asymptote. Personally, I only call lines asymptotes, but basically, whatever corresponding parabola you get for this polynomial piece, that is the graph that this graph here in black will approach. So if you graph y equals the quadratic here, that is the parabola that this graph will approach in the long run. The fraction piece, again, would die and approach 0. All right. So hey, folks, what if we had 7th degree over 4th degree? In the long run, what would this look like? Y equals a 7th degree polynomial over a 4th degree polynomial. Overall, what would that graph look like? Well, the quotient is going to be 3rd degree. And you might get a fraction piece, like over here. Overall, it's going to be a snake. I'll make something up. Y equals, how about x to the 7th minus 4x to the 6th plus 4, okay, all divided by 3x to the 4th minus 2. I'll put a negative sign in front, just for kicks. How about that? 7th degree divided by 4th degree. In the long run, we get a snake. Here's a falling snake. It's a falling cubic. Well, it's going to approach a falling cubic in the long run. Okay, close to x equals 0. It's kind of messed up. It's not quite like a cubic over here, but in the long run, it's really going to resemble a cubic. If x is out to the plus or minus millions, billions, trillions, it's basically acting like a cubic. If x is close to 0, it might act less like a cubic. Like here, it's looking really flat. All right. Long run behaviors. We know everything now. In case 1, so let's review these cases. In case 1, y equals 1 over x, bottom heavy. The x-axis, y equals 0, is an HA. And it's the long run behavior of the graph. And the value of 1 over x in the long run approaches 0. 1 over, how about 2x plus 1 over 3x plus 3? That approaches a horizontal line. This time it's y equals what? Y equals 2/3, the ratio of leading coefficients. In the long run, that's how it behaves. In the long run, these values approach 2/3 as x gets more and more extreme. And we just talked about the top-heavy cases where it graphs like a bull or a snake. Because in the top-heavy cases, you know the quotient is degree 1 or higher. It's a non-constant polynomial quotient. In the long run, you're going to get either a bull or a snake, because the polynomial piece will be either degree 1, 2, 3, 4, 5, or so forth. Non-constant polynomial. Bulls and snakes, once again. All right. So in the long run, the graph of any rational function, will either approach a line, a bull, or a snake in the long run. A line, a bull, or a snake in the long run.
All right. Any questions? Any questions? Lots of information there. Any questions? Now, to celebrate HAs, horizontal asymptotes, I'm going to show you a clip. I'm going to show you clips from one of my favorite comedies of all time. It's become a documentary. It's called Idiocracy by Mike Judge, who did Beavis and Butthead. Many of you know this film. All right. So next up, we're going to discuss, what happens if it's not simplified. All right.
Hi, everyone. Before, when we were discussing VAs, we assumed that this rational expression was simplified, that they had no common factors, certainly not common factors in X. Now, bear in mind that HAs and SAs, horizontal and slant asymptotes, don't care about whether the expression is simplified or not. For example, HAs just care about the leading terms. Now, how are these different? Well, VAs deal with sudden explosions, like in the middle of a graph. HAs and SAs both deal with long run behavior, like as X approaches infinity or negative infinity. So in that sense, they study very different things. Now, they do have a few things in common. What are the few things they have in common? Well, in common, they're lines, right? An asymptote is a line that a graph approaches, broadly speaking. In particular, we draw them as dashed lines, and they involve ideas of infinity. But beyond that, these actually have surprisingly little in common. VAs deal with sudden explosions in the middle of a graph. HAs and SAs deal with long-run behavior. And the way we obtain these is very different. And again, VAs care about whether this is simplified. HAs and SAs don't. Now, what if this is no longer simplified? What if n of x over d of x is no longer simplified? In particular, what if they have real zeros in common? Then, it's possible that at such a common real zero, we could have a VA, or we could have a hole. This is something we haven't seen yet in this section, because if the given expression is simplified, you're not going to get holes. But if the given expression is not simplified, you could get a hole, where you have a real zero in common. All right, here's an example. Graph y equals, or f of x equals, x squared minus 9 all over x minus 3. You may be itching to do what to the numerator? How about factor it? let's factor the numerator. And what do we get? We get x plus 3 as a factor times x minus 3 as a factor. And what can happen? These cancel out, they divide out to 1. By the way, something you may have observed that 3 is a real 0 for both the numerator and the denominator. If you plug 3 in for x in the top and the bottom, you get 0 on the top and the bottom. So notice that 3 is a real 0 of both the numerator and the denominator. So what do we have at x equals 3? At x equals 3, you know, before, when we had like 1 over x minus 3, we knew we had a what at x equals 3? We knew we had a VA. But here, since this is not simplified, it turns out that there could be a hole. So right now, at x equals 3, we can say that there will either be a VA, a vertical asymptote, or a hole. It's going to be one or the other. But which is it? Are we going to get a VA or a hole? All right. Bear in mind that if 3 had not made the denominator 0, then we would have had a point, a bona fide point. All right. So these cancel out, and we're left with x plus 3. But now, remember something we talked about early in the course. X cannot be what number? X still cannot be 3. If 3 was an illegal value for x back here, we have to make sure to remind ourselves that 3 is still illegal over here. We have a hidden restriction. Do not forget your hidden restrictions. If you have a hidden restriction like this, very often that leads to a hole. And in fact, here, it will lead to a hole. We're going to get a hole on a VA. All right. Because if the restriction were obvious, it would be a VA after the simplification. If you need a hidden restriction, then you're probably getting a hole. All right, so what do we have here? I'm claiming that x squared minus 9 all over x minus 3 is equivalent to this expression, x plus 3 with the hidden restriction that x cannot be 3. So how would you graph y equals this fraction? Well, you would graph basically y equals x plus 3. How would you graph y equals x plus 3? It's a slanted line, right? Here's our old friend, y equals x plus 3 as a slanted line. And ordinarily, the point 36 would be on the graph if we had the line y equals x plus 3. But now, wait a minute. We're saying that x is not allowed to be 3. So actually, if you're going to graph y equals this original fraction here, we're not allowed to have a point with x coordinate 3. So technically, we're supposed to have a hole there. The graph of y equals x squared minus 9 all over x minus 3, it looks like this. It's the graph of y equals x plus 3, but since 3 is not in the domain of the function, we're not allowed to have a point with x coordinate 3. We have to pluck the point 3, 6 out of the graph, and we're left with a hole here. The official terminology in calculus is that we have a removable discontinuity at x equals 3. In the sense that it's easy to think of a related function where you fill in that hole. Personally, I think that's a bit of a misnomer. You don't have to write the fill in the hole because you feel like it. Right. But we have a removable discontinuity at x equals 3. We have a hole. It's a hole, not an open endpoint, because we have neighbors immediately to the left and neighbors immediately to the right. It's a hole. Now, by the way, you're smarter than Desmos. If you ask Desmos to graph y equals this, what happens? Y equals, parentheses, x squared minus 9 over, parentheses, x minus 3. I'm putting the parentheses to be safe. Now, wait a minute. You might be saying, well, hey, this just looks like the line y equals x plus 3. So Desmos might be tricking you here. But you know what? This is why you need a human operator. Desmos is not being honest with you. Desmos really should be clearly indicating a hole there. If Desmos gave me this for a homework answer, I would mark Desmos wrong. You hear that, Desmos? I would mark you wrong. Although, to give Desmos credit, if you try to click on the point where, if you try to click on the point where 3, 6 would have been on the graph, see here, at least when you click on the point 3, 6, Desmos does admit that the function value is undefined there. But you have to click on 3, 6 in order for Desmos to tell you that. If you don't do that, just by looking at this picture, you wouldn't know that there's supposed to be a hole at 3, 6. You have to actually click on the graph for Desmos to remind itself that there's supposed to be a hole there. Okay, so you're smarter than Desmos. Desmos should be putting a hole there, and it's not. Okay, so on homework, you should be doing something like this. Draw the line, but clearly indicate the hole here. All right, now why do we have a hole? Well, good question. Why do we have a hole? Why do we have a hole at x equals 3? Okay. First of all, why do we have a hole and not a point? Because 3 is not in the what of this function. 3 is not in the domain of the function because x equals 3 would give us a 0 denominator. 3 is not in the domain of f, so we can't have a point on the graph with x-coordinate 3. Okay, the point 3, 6 is not allowed to be on the green graph because 3 is not in the domain of the function. So we know we cannot have a point on the graph. Notice x cannot be 3. 3 is not in the domain. Now, algebraically, why do we have a hole? It's because the corresponding factor, x minus 3, gets completely canceled out. The factor, x minus 3, is completely canceled out or eliminated in the denominator. We started off with an x minus 3 factor down here, all right? But it gets completely canceled out by the x minus 3 factor up here. By the way, one consequence of the fact that 3 is a real 0 of both the top and the bottom, that means that x minus 3 must be a factor of both. So 3 is a real 0 of both the numerator and the denominator. One implication of that is that by the factor theorem, x minus 3 is a factor of both. So if you notice that 3 is a 0 of both the top and the bottom, that's a hint to help you factor. That means x minus 3 is a factor of both the top and the bottom. And that turns out to be true. That may help you factor this thing on top. Again, why do we have a hole? Because 3 is not in the domain of f, so we're not allowed to have a point on the graph there. And the corresponding factor x minus 3 is completely canceled out in the denominator. So here's the thing. Normally, if the denominator is approaching 0, we're in trouble. We might have a VA, or vertical asymptote situation, like a big sudden explosion. But because we have a twin, an x minus 3 factor up here, who ultimately destroys all the x minus 3 factors down here, the x minus 3 factor in the denominator is no longer a threat. It's like you're putting a robot over a bomb. The x minus 3 factor is no longer a threat. It's completely canceled for the denominator. And now, as x approaches 3, we don't have a problem of the denominator approaching 0 anymore. as x approaches 3, the denominator no longer approaches 0, and we're safe. Now, if x minus 3 factors do survive, we'll have a VA. We'll discuss that issue later on. How can we tell we have the whole at the point 3 comma 6? Well, it's a limit problem. To find the limit of f of x as x approaches 3, you take the simplified expression and plug x equals 3 into here. So 3 comma 6 is the hole on the graph, because when you plug in x equals 3 into the simplified expression, x plus 3, you end up with 3 plus 3, or 6. Remember, the limit value is the y-coordinate that you approach if you run towards this hole from the left and from the right. You're approaching a y-coordinate of 6, so it's the limit value. The function value at 3 doesn't exist, but the limit value exists. It's 6. So this function here approaches 6 from either the left or the right. If you acknowledge that there's a hole here, all right, then the y-coordinates approach 6. The function values still approach 6 from the left and from the right as x approaches 3. So to find the y-coordinate of the hole, you plug x equals 3 into the final simplified expression, and you get 6. That's the limit value. That's how you calculate that limit value in calculus. All right, so that's why we have a hole at 3 comma 6. Again, 3 is not in the domain of the function, so we're not allowed to have a point on the graph. That means we either have a hole or a VA. How do we know we have a hole and not a VA? Because the factor x minus 3 down in the denominator is completely canceled out. It's completely eliminated. So it's no longer a threat as x approaches 3. All right, next we'll talk about the VA case.
All right, any questions? Any questions? Well, there's no VA, right, but Desmos should have put a hole there. It really should have. But then how would it do zooming? That might be kind of tricky, how to do zooming. Yeah. All right, any questions? Any questions? All right.
Hi, everyone. Let's consider y or f of x equals the fraction x minus 2 over x squared minus 4x plus 4.
Actually, you know what? I'm looking over things. Let's take a break now. We'll get to the VAs after the break. So I have 8:15 right now. Let's come back at 8:26, and we'll discuss the VA case and an overview, all right? So let's come back at 8:26. Right. Break until 8:26 p.m. Duh. Mute. Record. All right. So see you then. All right. Any questions? Any questions? Okay. So let's rewind this a bit. When do we have VAs? All right. Let's do it.
Hi, everyone. Let's consider y or f of x equals the fraction x minus 2 over x squared minus 4x plus 4. Some people may observe that 2 is a 0 of both the top and the bottom. And what does that mean? 2 is a 0 of both the top and the bottom. So that means that x minus 2 is a factor of both the numerator and the denominator. Now, you don't have to observe that this early on, but I just wanted to make that comment, that since 2 is a 0 of the top and the bottom, it's a common real 0. That means that x minus 2 is a common factor for both the top and the bottom. Again, you don't have to observe that now. You can factor the bottom, and you'll see this happen. How do you factor x squared minus 4x plus 4? Again, this is a hint. This turns out to be a PST. it didn't have to be, but this does turn out to be a PST. It is, in fact, the square of x minus 2. So when you factor, you get this. X minus 2 over the square of x minus 2. This is clearly not simplified because x minus 2 is a common factor in x on the top and the bottom. So what can we do? We can cancel out or divide out a pair of x minus 2's. We have one x minus 2 factor on top. That's a way of looking at it. We have one x minus 2 factor on the top in the numerator, and we have two x minus 2 factors on the bottom in the denominator. So one factor up here can cancel out with one factor down there. And when we simplify, we still have one of these x minus 2 factors surviving down below. So I want to note that algebraically, this expression here is perfectly equivalent to this expression over here. There are no hidden restrictions. There's an evident restriction right here. We know x cannot be 2. This is an evident restriction. Evidently, x is not allowed to be 2 because that would make the denominator equal to 0 in the simplified expression over here. It's evident. So it's evidently a problem when x is approaching 2. That means we're going to get a big explosion, and that means we're going to get a VA. Okay, now here's the deal. Because we have a graph for a rational function, at x equals 2, there are three possibilities. We're either going to get a point on the graph, or a hole, or a VA. So at x equals 2, we're either going to get a point on the graph, or a hole, or a VA. But wait a minute, I know that we're not going to get a point on the graph. Why not? 2 is not in the what of the function. It's not the domain, because it makes a denominator equal to 0. So right here, because 2 is not in the domain of f, 2 is not in dom of f, that means that we cannot have a point on the graph. 2 is not the domain of the function. We're not allowed to have a point on the graph of f. Now, why don't we have a hole? Why don't we have a hole? And why is it that we have a VA? Because the corresponding factor x minus 2 ends up surviving. The problem factor, as x approaches 2, is x minus 2. See, if x is approaching 2, the problem is that that bottom is going to be approaching 0, and that's a potential problem, right? And this factor survives. In the simplified expression, after you do your cancellations, in the simplified expression, an x minus 2 factor survives in the denominator. So it's still a problem. And we're going to get a huge explosion, and that leads to a VA. So as x approaches 2, this x minus 2 factor up here, this robot, it valiantly tried to save us from a big old explosion, but it failed. We needed 2 or more robots. We only had 1. We had these 2 bombs over here. One robot did knock out one of the bombs, but we still have that second bomb that survived down here. As x approaches 2, that bottom is still approaching 0, which means we're going to get a huge explosion. If the top is a number, is a non-zero number or approaches a non-zero number, and the bomb's approaching 0, if the top is approaching a non-zero number, if the top is approaching a non-zero number and the bottom is approaching 0, we have a problem. We have a problem. We're going to get a big old VA on this rational graph. So that's why we have a VA and not a whole, because the problem factor, the x minus 2 factor, still survives there after we simplify and cancel. So because of this, we have a VA and not a whole. For the graph of a rational function, you cannot have both a whole and a VA. In general, you can. I mean, you can have a messed up graph like this. Actually, it would be more like an open endpoint, I guess. It'd be more like an open endpoint. But
I mean at the same x value. You can't have a whole and a VA at the same x value.
it's more of an open endpoint. We could have something like that for a function. The thing is, though, a guy like this would not be rational. Right. For a rational graph, you can only have one of these at x equals a given real number, either a point on the graph or a whole or a VA. It's one of these three. If you don't have a rational graph, you could have various things going on.
Okay, any questions? Any questions? We're going to do an overview right now. Okay, because let me go back to the previous video here. Yeah, okay. So why isn't it a whole? Because, well, basically you can either have a point, a whole, or a VA, right? So why do we have a VA? The question is, why do we have a VA? And therefore not a whole. It's because the problem factor, x minus 2, survives in the bottom, in the denominator, after you do your simplification. So x equals 2 gives us a VA, not a whole. Again, the problem is that when you look at the simplified expression here, as x approaches 2, the bottom approaches 0. Now, if the top is like a 1 or something, if the top is not approaching 0, it can't do anything about that. The fact that x minus 2 is approaching 0. That's a problem. We get a huge explosion. All right. And, you know, by the way, I'm going to do an overview right now. Let's do that, and that may help.
Various things going on. Hi, everyone. Here's the graph of y equals 1 over x minus 2, by the way. It should be a familiar friend, right? It has a VA at x equals 2, as we've said. This is the graph of both y equals this over here and y equals this over here. These are equivalent expressions, perfectly equivalent. If you graph y equals 1 over x minus 2 on Desmos, we see we have a VA at x equals 2. This blue line, it should be dashed. Right? It's a horizontal translation of our classic y equals 1 over x. All right, so if you have y equals a rational expression like this, polynomial over polynomial, if it's not simplified, what's the deal? So if this thing here is not simplified, then the real zeros of the denominator can correspond to VAs or wholes. And to figure out which you're going to get, it helps to do things like factor and cancel. You have a VA if the problem factor still survives in the bottom. If x equals, okay, if you have a question about x equals 2, the problem factor is x minus 2. If you have a question about x minus 3, the factor is x minus 3.
Well, if you have a question about x equals 3.
Okay, so now, oh, by the way, more about this graph. Also notice there's an HA. Where? At the x-axis, because it's bottom heavy, y equals 0. We should indicate the horizontal asymptote as well. Again, the purple HA should be dashed. In the long run, it looks like a cross. If you zoom out, it looks like a cross, the HA and the VA. All right, so here's an overview. Comments on graphing rational functions. Assume we have y as a function of x. Y equals f of x. Well, first of all, the biggest issue is to determine the domain of f, right? So if you have something like y equals 1 over x squared plus 1. That was this bell shape over here. Domain was all real numbers, and we had no VAs or holes or anything like that. Every real value of x corresponded to a point. The domain was all real numbers. But if you do something like remove the plus 1 from the denominator, look what happens. Our dormant volcano explodes, and we have a VA at x equals 0, which corresponds to the real 0 of the denominator. Before, with 1 over x squared plus 1, there were no real zeros for that bottom guy, so we never had a domain problem, and we had no VAs or holes. So that plus 1 down there made all the difference in the world. Find any VAs, HAs, and holes. Now bear in mind that VAs and holes are related because you have to wonder if you have to simplify the expression, right? Simplify the expression to see what's going on. HAs and SAs are actually more related. HAs and SAs, again, deal with long-run behaviors. I made these comments up here. Remember, VAs correspond to sudden explosions versus, these are very different, HAs and SAs deal with long-run behavior. VAs care about simplification, HAs and SAs do not. So they don't care so much about factoring and all that. Okay. Remember that graphs of rational functions, like polynomials, they don't have cusps or sharp corners, such as the absolute value graph. In between VAs and holes, they kind of look like polynomials. In between VAs and holes. They kind of look like polynomials. Okay, find intercepts. Remember the y-intercept, if any, tends to be easier. If 0 is not in the domain, then there is no y-intercept, right? But if there is, the y-intercept is easier to find. X-intercepts tend to be harder because you have to solve an equation usually. Solve the equation f of x or y equals 0. So it's usually harder to find x-intercepts. By the way, you might have none, 1, or a whole bunch. Even odd, you may be able to exploit symmetry. And another trick that also works with polynomials, long-run behaviors, the zoom out property. In particular, if the degree of the numerator is less than the degree of the denominator, okay, then you have an HA at y equals 0. In fact, as long as it's not top-heavy, you have an HA period, okay? As long as it's not top-heavy in degree, you have an HA. But if you have the top-heavy case, where the degree of the numerator is greater than the degree of the denominator, then you do the long division, and in the long run, you get like a bull or a snake. Maybe a slanted line, in which case you have a slant asymptote. That's if you're top-heavy by 1 in degree. Okay. But in the long run, I've said this before, a rational graph will look like a line, a bull, or a snake in the long run, if you really, really zoom out. Like a polynomial. A rational graph will look like a polynomial in the long run, if you zoom out. Where can a rational function change signs? Where can you go from being above the x-axis to being below, or vice versa? Well, like with polynomials, it could be at an x-intercept or at a real 0. But now with rational graphs, you may also have an issue with a VA. or with a hole that might happen to be on the x-axis. By the way, a hole on the x-axis does not count as an x-intercept.
Any questions? Any questions? Talking about graphing rational functions. So I hope that was an overview. Any questions before we go on? Any questions? That was the last one for 2.6. Then we have 2.7, which finishes the chapter. Any questions? All right.
Hi, everyone. Back in section 0.12, we solved linear inequalities such as these. We usually had infinitely many solutions that we could write in interval form. Now we're going to solve nonlinear inequalities in section 2.7. Why is it in this chapter? Because we'll often ask about the signs of polynomial function values. A key application of solving nonlinear inequalities is to find domains of algebraic functions such as these, f, where f of x has this rule. Let's do example 1. Let f of x equal the square root of x squared minus 9. Find the domain of f. Well, when is this real? When is the output for this expression real? We get real outputs if and only if the radicand, in green here, is non-negative. The value of this is real if and only if the radicand, x squared minus 9, is non-negative, that is greater than or equal to 0. That's a polynomial inequality. It's a quadratic inequality. It's a nonlinear inequality. There are several different ways we can solve this, and you can pick your poison. You can pick whatever method you want here, but please show the appropriate work. All right, so the domain of this function is the same set, of real numbers as the solution set to this inequality. So to find the domain of this algebraic function, we have to find the solution set to this inequality, which will be the domain of the function. So now it comes down to this. Solve the nonlinear inequality. Here it's a quadratic inequality. X squared minus 9 is greater than or equal to 0. Now, here's what a lot of students do. A lot of students do this. A lot of students will say, okay, x squared minus 9 is greater than or equal to 0. Add 9 to both sides, and we get x squared is greater than or equal to 9. So then x is greater than or equal to 3. No. Many students do that, but this is wrong. Actually, it would have been okay if you had put the absolute value of x is greater than or equal to 3. Actually, that would have been okay. But since students tend not to think about absolute value, I really don't recommend trying to do it like this. So even though this looks like a good step, I don't think this is good for students. This tends to be bad for students. To isolate the square and write this, even though we often do that for equations. So we're going to focus on x squared minus 9. We want to do a sign analysis. It would really help to know what values of x will give us positive values for this, x squared minus 9, what values will give us 0 for this value, and what values will give us negative values for this, even though those will not be in the solution set. All right, method number 1. This is the oldest school method found in old algebra books, the Sidechart method. Again, we want to solve this nonlinear inequality. X squared minus 9 is greater than or equal to 0. The answer to that is basically the answer to this domain question. But it comes down to this. Now, what we're going to do in several of these methods is that we're going to factor that left-hand side. Remember, factoring is useful if you have a 0 isolated on the other side. When we factor x squared minus 9, we get the factor x plus 3 times the factor x minus 3. We're factoring a difference of 2 nice squares. So now we're down to this. And here's the principle. If I have two numbers and you care about their sign, wouldn't you agree with me that if you knew the sign of the first number and if you knew the sign of the second number, then you would know the sign of the product? That's the idea. So in the Sidechart method, you set up a number line, a signed number line for the x plus 3 factor, a number line with signs for the x minus 3 factor, and then you consider the product. So for the x plus 3 factor, we ask, where is that equal to 0? When x is negative 3. For lesser values of x, we know that x plus 3 is negative. For example, if we plug in x equals negative 4 or negative 10 or negative 1,000,000, sometimes it's helpful to plug in ridiculous values for x. If you plug in x equals negative 1,000,000, we know that x plus 3 is negative in value. So I put a bunch of negative signs up here. On the other hand, if x is greater than negative 3, if it's negative 2 or 0 or positive 1,000,000, then the value of x plus 3 will be positive. So I put a bunch of positive signs here. I do something similar for the factor x minus 3. The key difference is that this is 0 when x equals positive 3. But the sign chart pattern still goes minuses, and then 0 here, and then pluses. Negative, then 0, then positive. And then when you consider the sign of the product, well, 0 times anything real is 0. So we know that this product is 0 at x equals negative 3 and x equals positive 3. And then within each of these three windows, the left window, the middle window, and the right window, we ask what sign is the product. In the left window, a negative times a negative gives us a positive. In the middle window, a positive times a negative gives us a negative. That's true for all real values of x inside this window. In the right window, a positive times a positive gives a positive. So we know that the sign chart for this product, which is the same as x squared minus 9, by the way, it's equivalent. The sign chart for basically x squared minus 9 goes positive, then 0, then negative, then 0, then positive. All right. So then, which of these real values of x do we want? We want the values of x that make x squared minus 9 either what or what? Either positive or 0. Because of that bar, we do want the values of x that make that equal to 0. So what do we want? Well, these values of x give us a positive value for x squared minus 9. The endpoints here, the negative 3 and the positive 3, they give us zeros for x squared minus 9. So yes, we actually do want these since we do have the bar here. It's a weak inequality. We don't, however, want these values of x in the middle because they give us negative values for x squared minus 9. Again, x equals 3 is a 0 for x squared minus 9. We want x equals 3. And for all of the x values in the right window, that gives us positive values for x squared minus 9. We want those. So to repeat, what do we want? We want these values in the left window. We do want the negative 3. We don't want the values in this middle window. We want the positive 3, and we want the right window. this is the graph for this set here. So the left window corresponds to parenthesis, negative infinity, comma, -3, bracket, we include the -3. Union, remember we put union whenever we're skipping over one or more numbers on the number line. Then we restart at 3, we want the 3, so bracket 3, comma, infinity, which kind of corresponds to that right arrow there. So that is the solution set for this inequality, and therefore the domain for this function over here. Now, if you don't believe me, let's go to Desmos. Let's graph y equals the square root of x squared minus 9. Y equals the square root of x squared minus 9. What are the x coordinates we pick up on this graph? Well, we pick up x equals -3 and all the x coordinates to the left. We also pick up x equals 3 and all the x coordinates to the right. It's like a high-low game. So the x coordinates we pick up here are all these real values in here. That is the domain for the function, that algebraic function I gave you. Now, if that seemed kind of long-winded, I'm going to show you some shortcuts.
All right, any questions before we go on? That's the old school method, but I'm going to quickly go over, well, sort of quickly go over fast shortcuts. All right.
Hi, everyone. If you found the sign chart method to be too long-winded, I don't blame you. So let's try an easier method. Again, we're looking at f of x equals the square root of x squared minus 9. We want to know what the domain of f is. The domain of f will be exactly the solution set to this inequality, because this square root guy is real if and only if the radicand is non-negative. So we're solving this quadratic inequality. Well, in order to figure out where this thing is positive versus negative, it would help to graph y equals x squared minus 9. Well, how do you graph y equals x squared minus 9? It's going to be a parabola. So let's do that. Let's graph y equals the radicand. Graph y equals x squared minus 9. Graph y equals x squared minus 9. And we're going to need to know the x-intercepts. Where is y equal to 0? Where is this thing equal to 0? Here, you do want to add 9 to both sides. X squared equals 9, so x could be plus or minus 3. So when you graph y equals x squared minus 9, you should know that's a parabola opening upward. It's going to have x-intercepts at -3, 0 and 3, 0. Now let's analyze this thing. Again, what are we trying to do? We're solving this inequality. The task is to solve x squared minus 9 is greater than or equal to 0. This parabola is the graph of y equals x squared minus 9. Remember, the graph of an equation consists of all points whose coordinates satisfy the equation. For each of these x coordinates, in principle, you can read off the corresponding y coordinate of the graph. All right, so where is x squared minus 9 what? Where is it non-negative? That means positive or 0. I want to know where the y coordinate on this parabola. I want to know where the y coordinate is positive or 0. Over here, on this blue piece here, the y coordinates are positive. So I want these real values of x that give me these positive y coordinates. I want this left tail over here. Do I want the -3? Well, Yes, it's where the y-coordinate is 0. I do want where y, or x squared minus 9, is 0 in value. So I also want the negative 3. I want all these values for x. Do I want these values for x, including 0? Do I want these values for x? Well, these y-coordinates are negative in value. X squared minus 9 is negative over here. So no, I don't want that. This looks like a mouse, sort of. Over here, the value for y, or x squared minus 9, is 0. Yes, I want that. I have the bar there. It's a weak inequality. And for these values of x, we get positive values for y. And I want where the y-coordinate is positive, or 0. So I want all these values over here. Of course, this corresponds to the same set that we got from method 1. This is the solution set for the inequality over here, and it is the domain for this algebraic function, once again. Another way to see the relationship, let's graph y equals the radicand, x squared minus 9. All right. So over here, for these very negative values of x, on the red graph, the y-coordinate, the value of x squared minus 9 is positive. The square root of a positive is a real number, so we're good. These values of x are in the domain. We get a real result. Real y-coordinates on the green graph. Remember, x is in the domain of this square root guy if we have corresponding points on the green graph. Over here, well, the square root of 0 is 0. When x squared minus 9 is 0, this radicand is 0. The square root of 0 is 0. Remember that y equals x squared minus 9 will have the same x-intercepts as y equals the square root of x squared minus 9. These guys have the same real zeros. They have the same x-intercepts. They share the same x-intercepts. That's true for negative 3, 0, and for positive 3, 0. They share the same x-intercepts. They're 0 at the same time with the same values of x. Again, on the red graph, on the red parabola, when the y-coordinates are negative, we're trying to take the square root of a negative number. That's no good. These values of x near 0 will not be in the domain of the square root guy because the radicand would be negative in value. Over here, again, the square root of 0 is 0. That's cool. And over here, for these values of x, we're getting positive values for y. That is x squared minus 9. Therefore, the radicand is positive here. We're good. So again, what are the valid x-coordinates for the green graph? When the y-coordinates on the red graph, the values of the radicand are either positive or 0. Now, you might ask, well, wait, what if we don't have a quadratic? What if we have a cubic, or a 4th degree, or a 5th degree? Well, then, I hope you paid attention this chapter. Then the question is, can you graph the corresponding vole or snake using the methods of this section, this chapter? And then you want to know, well, can you find the zeros? Whoops. Graph vole or snake. Find the real zeros, which correspond to the x-intercepts, okay, like we did over here, negative 3 and 3. The real zeros corresponded to the x-intercepts. For a parabola, we know that we're either going to have a bouncing situation, right? Or we have two distinct x-intercepts. Or maybe we don't have any x-intercepts. That could happen too, right? Right. So here we have two distinct x-intercepts, right? We have cuts in both cases. If we had something like this, it would be a bounce, right? If you know the factorization, find the factorization, and then you can figure out things like cuts and bounces. Does the graph cut at an x-intercept, or does it bounce? Okay. Over here, we cut at both the x-intercepts. Sometimes you just bounce. Sometimes you have like a flying parabola or something, or bowl, and there are no x-intercepts whatsoever. All right. Oh, by the way, sometimes the solution set will be all real numbers or the empty set. That's often the case if you get a parabola that doesn't have intercepts, x-intercepts. All right, so the parabola method, or just in general, the graphing method, where you're graphing y equals the radicand. If you've paid attention to this chapter, this can go very fast. Imagine me not talking. You're just looking at the notes. Imagine me not talking. Next, we'll look at more numerical methods, which you may often use in calculus. And also, these extend well to rational functions in general.
Any questions? Any questions? Well, I find the graphing method, the parabola method, to be easiest with quadratic inequalities. You know, quadratics correspond to parabolas. But in principle, you can extend this to other bulls and snakes, third, fourth, fifth degree, whatever, as long as you can find the real zeros and get the factorization.
Hi, everyone. Let's say you want to solve this quadratic inequality, x squared minus 9 is greater than or equal to 0, but you don't want to think in terms of graphs. You're more of a numbers person. All right, so let's think about the real number line. For what real values of x will this left side be positive or 0? Now, a rational function can only change sign at its zeros, at the real zeros, which correspond to the x-intercepts, or where it's undefined. That is, where the graph has a hole or a VA. So for example, on the left, we have the graph of this third degree polynomial, y equals this third degree polynomial. It's a snake, a rising snake, in this case. Now, there are two zeros, as it turns out. Over here, and then over here. We have two real zeros. Now, these two real zeros are the only places where this polynomial function can change sign. Okay. So,
by the way, I should have said two distinct real zeros, because you do have like a double zero over here. Two distinct real zeros.
For a polynomial function, like this cubic, the real zeros, which correspond to the x-intercepts, are the only places where the function f can change sign. A lot of writing there. So for a polynomial function, the real zeros, which correspond to the x-intercepts, are the only values of x where the function can change sign, but it doesn't have to. So over here, at this real zero, this x-intercept, the function does change sign from negative to positive. Basically, you change sign when there's a cut at the x-axis. You change a sign when the graph cuts through the x-axis. Here we're cutting through from negative y-coordinates to positive y-coordinates. But then, at this x-intercept over here, which corresponds to a real zero, we get a bounce. We don't get a cut, we get a bounce, which means that we don't change sign. For these values of x, y is positive, and for these values of x, y is positive. So for a polynomial function, the real zeros, corresponding to the x-intercepts, are the only places where the function can change sign. You get a cut here, but it doesn't have to. You might get a bounce. Now, if you have a rational function in general, well, again, it could change sign at x-intercepts or real zeros, but you can also change sign where it's undefined. So for a rational function in general, like for the reciprocal function given by 1 over x, here's a graph of y equals 1 over x. Here, we change sign across the VA. The function value is negative here. We have a VA like a river when we cross the river. Here, because the exponent on x is 1, it's an odd VA. So when we have an odd VA, when the exponent on the factor down there is odd, we have a change in sign. For an even VA, we don't have a change in sign. Remember, y equals 1 over x squared. sorry, y equals 1 over x squared, right? We don't change sign. Positive here, positive over here. That's if we have an even VA. Here we have an even VA. All right. Also, you can change sign potentially at holes that happen to lie on the x-intercept. Although, again, you don't have to.
On the x-axis, the holes that happen to lie on the x-axis.
All right. So again, where can a rational function change sign? At the real zeros or where it's undefined, like if you have a VA or a hole. But you don't have to change sign. You could have a bounce here, for example, or you could have an even VA, like over here. All right. So based on those principles, find the real values of x squared minus 9. Well, for the 10 millionth time, we get -3 and +3. These are like gates. They're like gates. We might change sign or we might not. So consider the real number line. X squared minus 9 can change sign at -3, and it can change sign at 3. We know that these are zeros for x squared minus 9. This is the sign of x squared minus 9. It's 0 at -3 and a +3. And then you can test values. You know the domain of a polynomial function is assumed to be all reals. We have 3 windows here, 3 windows. Bear in mind, for a general rational function, anytime you have a place where the function is undefined, you need another fence post. Here, we just have fence posts here where the polynomial is 0. If you have something like 1 over x, for example, you need a fence post at x equals 0, where it's undefined. All right. Now, in the test value or test window method, remember, x squared minus 9 only changes sign, potentially, at the real zeros. So test a value. For example, in the left window, test a value to the left of -3. For example, -4. Put a star here, -4. Although sometimes it's easier to use a ridiculous number like -1,000,000, right? But let's use -4. Plug a -4 into here, into x. What do you get? You get 16 minus 9, which is +7. I don't care that it's +7. I just care it's positive. I don't care it's +7. I just care that it's positive. Now, because x squared minus 9 is positive in value at x equals -4, it's positive in value all throughout this window. Because if it changed sign, we need another fence post. All right. We know it's 0 at x equals -3, x squared minus 9. What about here? 0 is the obvious test value for x. Plug in x equals 0, we get -9. That was why on that graph, 0, -9 was the vertex of this red parabola. All right. But I don't care that it's -9, I care it's negative. That's the key thing. The value of x squared minus 9 is negative at x equals 0. Therefore, it's negative at all other real values within this open interval between -3 and +3. So at x equals 1, 2, 2.5, -2.5, I know the value of this is negative. What about over here? Let's test +4. Or we could be cute and test +1,000,000, not to scale. +1,000,000. Plug in +1,000,000 for x. Obviously, 1,000,000 squared minus 9 is positive all throughout this window. And again, we're solving this inequality. X squared minus 9 is greater than or equal to 0. I want to know where x squared minus 9 is positive or 0. I'll put this in purple. I want to know where x squared minus 9 is positive or 0. I like it when x squared minus 9 is positive or 0, not when it's negative. I like it when it's positive, 0 or positive. So I want all these values of x over here, the left wing and the right wing, which corresponds to the same answer as before. It better. Method 4 is like a mix of like the Sidechart method and the test window method. So here, I'm plugging in test values for x, like -4, 0, and +4, or positive 1,000,000 maybe. But remember, I don't care about what the actual value of x squared minus 9 is. I just care about the sign. So you might want to consider the factored form, the factor x plus 3 times the factor x minus 3. For example, if you plug in x equals -4, or even more easily, x equals -1,000,000. We know that a -1,000,000 plus 3 is negative. -1,000,000 minus 3 is also negative. So when you plug in x equals -1,000,000, or x equals -4 for that matter, we're going to get a negative times a negative. That result is positive. Again, this is a hybrid of the Sidechart method and the test value method I just mentioned. Repeat the process. Again, we care where the product, x squared minus 9, which was this times this, we want where it's positive and where it's 0, not where it's negative. We want where it's 0, where it's positive, and again, we want the wings. Again, we want the wings, which was this set over here. Okay. Next up, some more examples.
Any questions? Okay, we're pretty close to the end, so let's go.
Hi, everyone. Let's look at some variations. For example, let f of x equal 1 over the square root of x squared minus 9. So when is this real? I want to know the domain of this function. Find the domain of f. I want to know the real values of x for which this is real. When is this thing real? This thing is real if and only if the radicand is what? Strictly positive. It cannot even be 0. You're not allowed to divide by 0. The radicand must be strictly positive. So we have to solve this strict inequality. X squared minus 9 is greater than 0. No bar. So how does our domain change? How is the solution set different from before for this inequality? You exclude the endpoints here. So you have parentheses next to the -3 and the +3. Let's look at the graph of that. What is the graph of that thing? Y equals 1 over the square root of x squared minus 9, right? Look at this. It turns out we get VAs at x equals -3 and x equals +3, right? The domain, again, we get these very negative numbers. We get these very positive numbers. We don't get the numbers near 0, and we don't get 3 and -3 themselves. We have VAs there at x equals 3 and -3. And we have open parentheses for the domain. What happens with our various methods? All right. Well, in the Sidechart method, I don't want the actual endpoints at -3 and +3. I don't want where the product is 0. In the problem method, I don't want the x-intercepts. I don't want the 3 and the -3. Don't want these. In the test interval method, I don't want where x squared minus 9 is 0 itself. But I still want the wings. We want open parentheses here. Same for this. All right. But that was the difference. Open parentheses. We don't want where the radicand is 0. Trick question. F of x equals the cube root of x squared minus 9. Quick. What's the domain? The domain, implied domain of the domain of an odd root of a polynomial is assumed to be all reals. No restrictions. Because the domain of a polynomial is assumed to be all reals. And cube roots never cause a problem. Whether the radicand is positive or 0 or negative, the cube root's fine with that. For example, the cube root of -1 is -1. The domain is all reals. Hey, if g of x is the 11th root of a 40th degree polynomial, what's the domain? It's all reals. We love odd roots of polynomials. Of course, whenever the radicand's messed up, it's messed up. If you have the cube root of 1 over x, say bye-bye to x equals 0, but that's not a polynomial. All right. Look at this now. Let's say that I ask you to solve the inequality x squared is greater than x. I want to know all real numbers whose squares are greater than themselves. Now, a lot of students are thinking, hey, I'd love to divide both sides by x. Do not do that. Do not divide both sides by x. That's very risky. Why? If x is negative in value, what do you have to do to that symbol? You have to flip it. So in order to do that, you might have to split into cases where x is positive, where x is 0, where x is negative. So just in general, it's a bad idea to divide both sides by a variable expression, unless you're sure it stays positive. Right. So instead of doing that, let's isolate 0. Subtract x from both sides. Isolate 0 on the other, and then it becomes a sign analysis problem. We like turning things into sign analysis problems. Factor, and by the way, we have to factor over the reals, right? We're factoring over the reals. Because when you consider the potential x-intercepts, every real 0 corresponds to an x-intercept. So we want to factor over the reals. Right? Factor over the reals, we get x times the quantity, x minus 1. All right, put parabola method. The graph of y equals this guy or this guy, the factored form, parabola opening up. The x-intercepts are at 0, 0 and at 1, 0. I want to know where the values of y equals x squared minus x. I want to know where the values of this thing are positive. So I want to pick up, I'll make this piece hairy. I want to pick up the pieces of the parabola that are strictly above the x-axis, not the intercepts themselves. There's no bar here. So I want to put open circles here. I want the real values of x that are negative or greater than 1. Negative or greater than 1. This is the solution set to both these inequalities. And this makes sense. Intuitively, it makes sense. You could use the test value method. Okay, we want numbers whose squares are bigger than themselves. Well, of course, if you take a number like 1 million, the square of a million is bigger than itself. We want these numbers. But the square of 1 is equal to 1. It's not greater than 1. I don't want the 1 itself. Likewise, the square of 0 is 0. The square is equal to itself. I don't want the 0. Now, what about 1/2? The square of 1/2 is 1/4. But wait, 1/4 is not greater than 1/2. I don't want these values either. But wait a minute. The square of every negative real number is positive, isn't it? Every positive number is greater than every negative number. For example, the square of -3 is greater than -3 itself, because the square of -3 is positive 9. Every positive number is greater than every negative number. So all the negative real numbers work. Intuitively, this makes sense. We want all negative real numbers and all positive real numbers greater than 1. Numbers like 1/2, their squares are less than themselves. All right. And again, in really weird situations, you might get all real numbers or the empty set. For example, the square root of opposite x squared. The domain for that is the empty set. You're just dead everywhere. Actually, not everywhere. Oh, I should have done this. Because x equals 0 would have worked. There you go. For all real values of x, this thing is guaranteed to be negative. The domain for this thing will be the empty set. All right. That's chapter 2.
But let's have some fun with Desmos, and then that's it.
Hi, everyone. Just some fun with Desmos. Where is x squared greater than x? Well, let's graph y equals x squared. Let's graph y equals x. When is the y coordinate on the green graph higher than the y coordinate on the purple graph? All right. Well, the green graph is higher for negative real values of x. The green graph is higher for real values of x greater than 1. But between 0 and 1, okay, the green graph falls below the purple graph, and at x equals 0 and at x equals 1, you have intersection points. These are equal. So the graphs verify the solution set to this inequality. This over here, if you try to graph that thing, y equals the square root of the opposite of x squared plus 1. Hey, where's the graph? Where's the graph? Empty set. It's a null graph. There's no graph because the domain is the empty set. No graph. It's a null graph. And by the way, this guy here, domain is all real numbers. I'll show you. Y equals x squared minus 9. I want a cube root, so 1/3, right? Kind of funky looking, but yeah, domain is all real numbers. Domain is all real numbers. We pick up all real numbers as x coordinates. That's the domain for this over here. And like I said, hey, y equals, if I take any polynomial, x to the 17th plus 7x to the 4th minus 2. Let's take the 5th root, all to the 1/5, whatever. This funky looking thing, all real values are picked up as x coordinates. Domain is all real numbers. The 5th root of any polynomial, domain is all real numbers. Play with Desmos, it's fun.
All right. So that is that.
Let us suppose that
Have a good weekend, but I'll stick around for questions. And by the way, the general consensus seemed to be that people wanted me to keep recording the questions and answers. I think a lot of students appreciate that. But again, if you really want privacy, go ahead and chat to me, maybe privately, that you want me to pause the recording, and that's fine. But generally speaking, I think the students want me to keep recording so that they can capture some of the question and answer sessions. Okay, so for some of you, we're done through 2.7, chapter 2. So if you're following the notes, you can get through all of chapter 2 by Tuesday. Please keep up. I can finally start grading soon. That'll help. Okay. In the meantime, I'll stick around for questions.
I have a question on which one was it? 2.18b. I was just wondering, like, how do you know which formula to use?
2.1, sorry, 2.1 what? 1b?
8b.
8b. Oh, okay. So, so the idea is that, all right, so the profit function is an upside down parabola. So the key point of interest is going to be the vertex, okay? And the vertex is going to indicate when you're maximizing profit. So B, use a formula to find the number of widgets produced and sold for which profit is maximized. How do you get the x coordinate? That's our formula for x, or h. H equals the opposite of b over 2a. It's that piece of the quadratic formula. That's the formula I'm referring to. The x-coordinate, or h, is given by the opposite of b over 2a. How do you get the y-coordinate? Plug it in. So basically in 8 and 9, I'm asking you to interpret, for them, for B and C, I'm asking you to give coordinates for the vertex.
Okay. Yeah, I got the rest of it. I even got that question right. I was just wondering like how, like where that formula like comes from and like why it's used to find that basically.
Yeah, it's from the quadratic formula. And the deal is that, okay, how do we find the x-intercepts, right? Well, the real zeros correspond to x-intercepts here and here. Well, what formula gets us the zeros, whether they're real or not? The quadratic formula, right? We have a plus case and a minus case. One of those cases gives us that. One of the cases gives us that. But where's the vertex? If you have a parabola that has two x-intercepts, all right, then the vertex is going to have as its x-coordinate the average of these two guys, right? Now the QF normally goes the opposite of b, plus or minus the square root of the discriminant, b squared minus 4ac. Okay, that gives us this number and this number. But what's the average of these? You just zap all this stuff, and you can pop this guy on the outside. So the reason why this works is that the x-coordinate for the vertex is given by the average of the x-coordinates for the two x-intercepts, assuming you have two, and these correspond to the real zeros, which can be found using the quadratic formula. Questions? Or can I clarify? Questions?
I got it now. Thank you. And I also.
Oh, and by the way, I think I do make mention of this in 2.1. I think it's like you're near the end. It's like side notes. Yeah, go ahead.
2.2, I don't really understand how to do 5, 6, or 7.
Right, the theory problems. All right, so let's discuss these. Number 5, how many distinct or different real zeros can a 4th-degree polynomial have? Okay, and I can show you different ways of looking at it. In fact, the answer is going to be, well, 0 up through 4, okay? Remember, the number, a 4th-degree polynomial function has 4 complex zeros, okay? So you can have at most 4 distinct real zeros. You can't have 5 or 6, all right? So at most we have 4. And in fact, I can construct various scenarios by the factor theorem. Okay, so for example, here's a guy with one real zero, right? X minus 1 has a 0 at x equals 1, and that's it. Here's a guy with 2 real zeros, okay, in factored form. This guy has zeros at x equals 1 and x equals 2. This guy has 3 real zeros. Oh, but wait a minute. It says 4th degree, right? X minus 1 to the 4th. Okay, that has one distinct real zero. 1 with multiplicity 4. I forgot we need 4th degree. All right. What about 2 distinct real zeros? X minus 1 and x minus 2 multiplied together. Maybe this is, let's see. Maybe this is cubed, for example. This is the first power. This is cubed. And that ends up being 4th degree. So we're using the factor theorem. How about this guy? Our real zeros are 1, 2, and 3. Whoops. Square this guy, for example, and the whole thing's 4th degree. In order to adjust the degree, basically manipulate the exponent. Finally, how about 4 distinct real zeros? Let's do another factor. Throw in an x minus 4 factor. And this has 1, 2, 3, and 4 as distinct real zeros. So by example, I've given you examples of 4th degree polynomials in factored form for 1, 2, 3, or 4 distinct real zeros. Can you give me a 4th degree polynomial with no real zeros? No real zeros. How about x to the fourth, what? I want a fourth degree guy such that when you graph y equals this guy, there are no x-intercepts. Y equals x to the fourth, what?
+1.
Plus 1. Or plus 2, or plus 3, or plus pi, right? Do I have Desmos here?
Yeah.
Yeah. Right. Y equals x to the fourth plus 1. I don't see any x-intercepts, no real zeros. Whereas, let me show you my other examples. X minus 1 all to the fourth. This is fourth degree. We have exactly one real zero. X minus 1 times x minus 2 all cubed. That's fourth degree. Oh, it's kind of a close call here. And we have two distinct real zeros. How about three distinct real zeros? Let's tack on x minus 3, and that's squared. We have three distinct real zeros. Whoops. And then finally, x minus 1, x minus 2, x minus 3, x minus 4, x equals 1, x equals 2, x equals 3, x equals 4. We cut. In the long run, it's a bull. It's more like a W. All right. That's a good theory question. Oh, yeah, and see if you can sketch graphs for the different cases. Yeah. So you demonstrated that. Question number 5. Question number 5. All right. On number 6, write a fourth degree polynomial in x in factored form that only has -3, 0, and 5 as its zero. So similar theme. Okay, so this over here. So if -3 is a zero, then x plus 3 is a factor. If 0 is a zero, what has to be a factor? If 0 is a zero, then x is a factor. If 5 is a zero, x minus 5 is a factor. But tell me, if I were to multiply these all out, or as it stands, what's the degree of this thing, though? What's the degree of this? The degree of this is only 3. How can I make it fourth degree? What can I do? What can I do?
You can square one of them.
Any of them, right?
Yeah.
Okay. Now, someone might ask, why don't you throw in like an x minus 1? That's going to throw in another 0. Can't do that. It's got to be an exponent. All right. So one of these guys has to be squared. But it can be any one of these. So I'd accept this. I'd accept that. I'd accept that. And by the way, you can put any non-zero coefficient in front, and you're good too. You can put in a 2, 3, 4, 5, 6, -7. That's fine too. Questions about number 6. Questions about number 6. Number 7, write a polynomial in x in factored form such that its only zeros are, okay, -2 with multiplicity 2 and 4 with multiplicity 3. By the factor theorem, if -2 is a 0, what's a factor? X what? X plus 2, right? X minus -2, x plus 2. That has multiplicity 2. What does that mean? What do I do?
Square.
Square. Correct. Exponent. Then, because 4 is a 0, what do I need as a factor? X what? I have 4 is a 0, so what has to be a factor?
X minus 4 cubed.
Minus 4. Multiplicity is 3, so that's cubed. Right. And what's the degree of this polynomial? We have a second degree guy times a third degree guy. What degree do you think the product is? Fifth. Just like x squared times x to the third is x to the fifth, a second degree times a third degree is a fifth degree. Or two linear copies here, 3 linear copies here, multiply them all together, fifth degree. All right. Questions?
I have two more if no one else has any, because I've already asked a few.
So is there anyone else who has a question? Just to kind of mix things up. Okay, let me go to 228. Yeah, this is this one, right? Oh yeah, this is the next one. How do you like that? All right. Use the intermediate value theorem to show that if f of x is this thing, then f has a 0 between 1 and 2. Here's the idea. Here's x equals 1. Here's x equals 2. If I can show that f of 1 is positive and f of 2 is negative, or vice versa, right? What kind of point has to appear somewhere in the middle? An x-intercept, which corresponds to a real 0. So here's what you have to do. Evaluate or find f of 1. Also, find f of 2. And observe they have different signs. And then you can apply the IVT. Meaning you state these things. All right. Questions? Questions? All right. So let's go back. Okay. So who was asking the questions before?
It was me, Nick.
Nick. All right. Okay. So okay. Okay. So what questions do you have?
It's just on 2.3, number 7. I'm just wondering, like, in the answer you. Wait, hold on. I accidentally just scrolled all the way down. That you're supposed to put it over x plus 1. How do you like know to do that?
Okay, you're talking about number 7 here?
Yeah, like how do you know to put it over x plus 1? Like I know that you can factor that and make it. What did I get?
Well, by SOAP, right? You know how to do it by SOAP from chapter 0, right? It's a sum of 2 cubes.
Yeah. That's what I was getting to. I was just getting to the
Okay.
page.
So let's say, and this is not shocking at all for a student. Let's say you go, oh my gosh, I forgot the formula for factoring the sum of 2 cubes. I would totally understand as an instructor. Well, use your knowledge from chapter 2. Look at x cubed plus 1. What value for x will be a 0 for this polynomial? What value for x will make this whole thing equal to 0?
-1?
Yes. Let's put that in the dunk tank. I don't even need the rational 0 test or anything. You should just see, right? If x is -1, well, -1 plus 1 is 0. Okay, now here I'm telling you use synthetic division. Now be careful. You should write what in here? Missing terms. Don't just write 1 and 1. You need the missing terms. Or at least their corresponding coefficients. The coefficients here are 1, and then 0, and then 0, and then 1. It's not just 1 and 1. You need to have the coefficients for the missing terms in the middle. All right? We bring down the 1. Multiply. Add. Multiply. Add. Multiply. Add. Okay. So this tells us that -1 is a 0. If -1 is a 0, what's a factor? X
plus 1.
plus 1. Right. Notice same sign. And then how do we get the other quadratic? It's a cutie. The other quadratic trinomial. Well, we look at the coefficients down here. Read off the QT, the quadratic trinomial. What do we get based on those numbers?
X squared minus X plus 1.
Right. I'm going to just raise the 2. Right. And notice this would follow the SOAP rule. Okay. So the cube of x is x cubed, same sign, plus sign. The cube of 1 is 1. And then for the trinomial factor, okay, you square the first guy, it's x squared. Opposite, you take minus sign. 1 times x is x. AP, always plus. The square of 1 is 1. So I can easily see how people might forget the factoring formula, but if you understand these principles, the principles of the remainder theorem, synthetic division, SOAP, which helps out. Any questions? Or I can, if you wish, I could maybe wait for 1 or 5 minutes and then see if you have more questions.
2.3, 11E.
2.3, this one?
Yes.
Okay. Well, yeah, and that implies that we're kind of working on the others as well, right? I guess 3 works. I guess. So 3, right? There are no missing terms. Descending powers. 15, negative 52, 19, and 6. Bring down the 15. Multiply by 3, 45. Add negative 7. Multiply by 3, negative 21. Add negative 2. Multiply negative 6. Add happy face. We got a 0. Okay, you agree that works?
Yes.
Yes. Okay, now let's do the factorization. Ah, yes, yes. This could be a little tricky. Because 3 is a 0, we've established that 3 is a 0 by the remainder theorem, right? F of 3 is 0. F of 3 is 0. If 3 is a 0 and we want a polynomial in x, what's a factor? X what? Based on our work.
3.
Yes, x minus 3. Because 3 is a 0 by the remainder theorem, right? F of 3 is 0 by the remainder theorem. We know that x minus 3 has to be a factor by the factor theorem.
Oh.
Right? Now let's get the other factor. All right. Now, once again, a third degree divided by a first degree is a second degree. It's going to be another QT. 15x squared. I should put parentheses. 15x squared minus 7x minus 2. I think this was doable. All right. So I got up to there. Any questions? Any questions?
I got it. Thank you. That was excellent.
Oh, did you get it?
Yes.
Okay. And then I think I don't know. Does this factor nicely? I think 3. Yes, I think it factors nicely over the integers. Right. Right. Although if you're desperate, you can use the quadratic formula. Okay. 15 times x minus a factor, and then kind of bring it in. Okay. I think all 3 zeros will be rational. 3, and I think you get 2 rational zeros from here. All right. Questions? Questions?
$2.39.
2.3, number 9. Okay, yeah, the pattern here. You're extending from number 8. Based on the pattern you observed in the previous example, do this. All right. So first of all, it helps to do number 8, right? I'm going to write kind of small here. All right. We're divided by x minus 1. 1 goes in the dunk tank. 1x to the fourth. And then you have a bunch of missing terms, right? 0x cubed,
2 zeros.
0x squared, 0x, 3, right? X,
Okay.
0x to the third, 0x to the second, 0x, and then finally the negative 1. In your work, if you have these, you don't have to write out the x stuff in here, but you need these in your work.
Right.
All right. Bring down the 1, multiply, add, multiply, add, multiply, add, multiply, add. Beautiful. 4 ones. 4 ones. So this thing is going to be, well, a fourth degree divided by a first degree is what degree? Fourth degree divided by first degree.
Oh, just third degree.
Third degree. 1x cubed
Hmm.
plus 1x squared plus 1x plus 1. Yes. It's beautiful. Yeah, it is beautiful. Yeah, that's the result.
All right. Thank you so much.
You're welcome, yes. And by the way, to check it, you can multiply this by x minus 1. That's called telescoping, where you'll notice a bunch of cancellations. And you just get this big old guy, x to the fourth, and this straggler at the end, negative 1. By the way, let me answer your question. Number 9. Okay, so when you divide x to the fourth minus 1 by x minus 1, you get this. The powers of x from x to the third down to x to the 0, or 1. Now, what happens when you divide x to the n minus 1, where n is a positive integer, over x minus 1? I think our leading term is going to be what? X to the what? What is an nth degree polynomial divided by a first degree polynomial? What's the degree of the result? Degree n over degree 1. It's going to be x to the n minus 1. So that next power of x down. Plus, what's the next term? 1 what? 1 x to the what?
First degree.
Well, that's at the near the end, though.
Oh,
What's n minus 1 minus 1? N minus 1 minus 1. How do you simplify that? N minus 1 minus 1. N what? N minus 2. And then yada, 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 you do end up with the 1 at the end,
oh, okay. I see.
right? Well, we assume n is big enough, right? So what I'm doing is a generalization. From here, we got this, right? From the synthetic division, okay? Which means that if you look at this rational expression, you're inclined to think that this is correct. Now, sometimes you get tricked in a calculus class, but here, we're just extending from this example. And we're noticing, hey, in the bottom row, what are you seeing in this bottom row here? You're seeing a whole bunch of 1s and a 0s at the end. So that's ripe for strategizing.
Okay. Thank you.
You're welcome, yes.
I have no more questions. Thank you so much.
You're welcome, yes, yes. Any questions? Any questions? I'll tell you what, as you gather your thoughts, let's take a 3-minute pause as you gather your thoughts, and then we'll address questions at 9:55, all right? Thank you for your perseverance. Let's take a 3-minute pause, gather your questions for me. All right. Any questions? Pei Hong, it's just you and me. So if you have any questions, oh, well, I am recording unless you want me to stop. Any questions? All right. Well, have a good weekend. All right. Good luck with chapter 2. I should be available by email. Yes, take care. Take care. All right. Have a good weekend.